morning all. We've got now 14 participants. I think yesterday we had 16, so we're probably going to start now. So I hope you had a nice evening, as one said as well. So here is the program for today. From now on, you're going to look at the post-processing of the results of the simulation you ran yesterday night. If there has been some issues with the simulation, we've got some post-processing files that you could get. Then Juan is going to introduce how to use user subroutine in Code Saturn, because through the user subroutines you got access to all the capabilities of the code, or the features. Then you will work on another tutorial. So instead of the flow in a tube bundle, but conjugate its transfer is going to be added to this. And the idea is to restart from the simulation from yesterday night and to compute the flow, adding some temperature features. After the coffee break, there's another tutorial about optimization of the software and how to tailor the partitioning so that you get the best out of the performance of the code. So I think now it's Juan is going to discuss and to present the section about post-processing. So I'll leave him the floor.
Thank you, Charles. Can you hear me?
Me, yes.
Yes. Good.
Yeah.
I have asked. Excellent. So, morning, everyone. Yesterday, most of you managed to submit the job and left it running on the machine. So today, the first thing to do is to check simulation. So in the last pages of the tutorial from yesterday, you should have instructions on how to copy the files that were created. Before copying, let's see if I can share this. Doesn't seem to be working. Can you see my screen? Yeah. No.
Yes, we can.
Okay, so if you're logging into Archer, you should have result file from your run yesterday, which will have some sort of name like this, with the date, so the year, the month, the day, and the time. And inside you'll see you have a checkpoint file, directory, sorry, post-processing directory, and monitoring directory. These are basically your results files. Your post-processing directory is what you're going to load into Parallel. the same thing as what you did yesterday with the laminar tutorial at the beginning. And the checkpoint is the file that Saturn writes to be able to restart. So it has much more information than the post-processing, and it's also much bigger in size. So for those of you who have a very slow connection and don't want to spend a lot of time copying that, I would suggest that you just copy the post-processing file back to your local machine, the post-processing directory, sorry. If you see, your checkpoint directory is about 1.5 gigabytes, whereas your post-processing is only 388 megabytes. Okay. You're going to need your checkpoint for the next tutorial, but what I would recommend to you is first of all, check that the actual run completed. So you can do something like this, for example, if you use the tail command to show the last part of a file, and then you can put minus the number of lines that you want to show. So in this case, if everything went correctly, you will see that the last iteration is 30,000, iteration number 30,000. Then it tells you that it was writing the files and shows you some information on the last time step. So you should see minimum and maximum values of velocities around the 20, 30 values. And basically, nothing here should be zero. Okay, so if you see zeros somewhere, that means there's a problem. Also here, it shows you the averages that we discussed in the tutorial. So if you remember, all of these things are variables. So that's why you have this V here. And all of these ones are not computed variables. They're just averaged. So there's no resolution of any equations. It's just sum over all of these time steps. And the number of time steps that they have been averaged for is this number. Okay? So check first that have this. Okay, you can have this is quite a big file. This listing file, it has a lot of information at the beginning about their settings, about the periodicity and the partition. I will go through that after. And then you have the main calculation. That's so for every 25 iterations, you get a set of a block of information like this. So if you see something like this, if everything is fine, then you can copy this directory as it's explained in the tutorial to your local machine, and then you can load that post-processing results in ParaView and have a look at things like instantaneous fields of velocity or the average values or pressure, etc., etc., etc. Okay, so we're going to do that now. If you have any problems, of course, just raise your hands, ask a question, put it in the chat, or just talk to us. We're happy to hear your voices. If everything's right, or is in rows. The file that you need to check is the listing file, or which is just a soft link to the runsolver.log file. So either of those files will show you this. Another thing is I'm using Vim here to open a file, but you can also use Emacs If you want a graphical interface, you can use Emacs GTK, for example. If your connection is fast enough, you can copy everything. There's some people yesterday that had a very slow connection and had problems copying just the mesh file, which is half of the size of the checkpoint directory. So what you see here, what I'm doing is copying everything, and it's quite a big file. But just to visualize your results, you only need your post-processing directory, really. But if you want to keep everything, it's better. So if you're probably in the UK, you'll be fine copying everything. It just take a couple of minutes. But some people from different parts of the world here. So okay, so once you have copied your results, you can go to your post-processing directory, and you can just load the case that you want. So you see that you have a joining.case, a results boundary.case, and a results fluid domain.case file. By default, Saturn separates the fluid and the boundaries into different set of files. You can change that in the settings. You can put it all together in a single one, but it's easier for you because not all the variables are stored at the faces, at the boundary faces. So Saturn is cell-centered discretization, so only things that are necessary at the boundaries are stored, which in this case you can see which ones are these things like, well, this is your geometry file for the boundaries, and that's the partition file, and then you have the shear stress, the boundary stress, and in this case the Y plus. That's the only thing that are stored by default in the boundaries. Whereas for the fluid, you have all of these other variables, which are the ones that are actually solved. So you can load them in Paraview. Depending on how fast your computer is, this could take some time. It's quite a big file. If you get these output messages, don't worry about it. It's just because it's an old version of Paraview. Once you have that, by default, you get the MPI rank ID, which is showing you which processor each part of the domain was sent to, basically. And here you can change the color variable that you want. So you can use, for example, velocity, and should give you your instantaneous value for velocity in all the domain. So it seems like there's a couple of people that are having problems with the simulation, so we're going to give them 5 more minutes and we'll move to the next one. Anybody has any questions? Any problems?
Just one question. I see that there's only the results for the last time step. So if you want more intermediate results, do you have to put it in the, I mean, I've been looking at the GUI and there is the post-processing tab. There is something called writer, so it's there.
Yeah, there's two things in Saturn. There's the I'll show you. Basically, you have in Saturn you can have a writer, which is basically like an index to what is going to be written, and then for each writer you can have parts. So if you go to the post-processing, here in the tab writer, by default you have this make this bit bigger. You have the ID of the first writer is called results, and it's -1 by default. And here you can change all the properties for that writer. So you can change here the periodic output to every n time steps or every second, or you can use a formula if you want. So for example, if you don't want to, you want to write every 100 time step, but don't write the first 2000, for example, you can write it as a formula. But for every writer, you have mesh parts. So by default, as I was saying, you have a float domain and boundary, but you can create another one here. That would be, for example, if you want a part that is only, in this case, for example, the central cylinder, or if you want to see where the velocity is less than a specific value or something like that, then you have to associate which mesh to which writer.
Okay.
So it's a bit complicated because you have to do separate things, but in the end, by default, if you just want more, then you just put this here.
Okay, thank you.
And you can also change the format. So by default, we have inside format, which is for ParaView. You use that in ParaView, but you could have it in MET, or you could have it in CGNS, or you could even have it in CCM. If here is in red because we didn't install these libraries in the virtual machine. But if you get them, you can write this. Okay, so I think we should move on. So what I'm going to do now is talk a bit about the subroutines. Can you see the slides?
Yes.
Okay, great. So as I said yesterday, one of the main advantages of actually working with Code Saturn is that you can do pretty much everything that you want. So it's open source and it's very much modularized, so you can change just the bits that you want rather than having to write very long pieces of code. And so I'm gonna just talk you through the different parts of the basics of programming in CodeSaturn and give you some examples and for Fortran and C. And then you'll put that into practice in the next tutorial. So when you click on run calculation, or when you type the run case, or when you do the CodeSaturn run minus initialization, like what you did yesterday, the code goes into the SRC directory and compiles everything that is in there. So this is a specific way for CodeSaturn to know where to look for subroutines. And that would override the values that you have on the graphical interface. And you'll see that in your SRC directory, there's a reference and an examples directory. So we make the distinctions between what are user subroutines and what is the source code subroutines. Okay. All of the user subroutines start by CS_user, and they are all in reference. And some of them have examples, some of them don't. We're working on that, and they're in examples directory. So there's a long explanation in the user guide and also in the developer's guide of CodeSaturn. You should get those PDFs in your installation of CodeSaturn or on the website. So some of the basic subroutines that we have in CodeSaturn, I'll list them here. The first one is CS user parameters. There's two versions at the moment. There's the C part and the Fortran part. Originally, as I said before, the whole code was written in Fortran, and now it's slowly moving into C. So that's why you have some functions that are in CS user parameters Fortran, and another one that is in CS user parameters.c. But here is where you set pretty much everything from your numerical parameters, your time step, your equation resolution, tolerance, etc. And also your main physical parameters, your density, gravity, things like that. And you have CS user boundary conditions, which, as the name implied, sets the boundary conditions. But it's much more powerful than your graphical interface. In the graphical interface, you can choose from the preset types of boundary conditions, whereas in your subroutine, you can put whatever you want. This is normally very useful when you have things like inlet profile, for example, or a time varying function that you want to implement for an inlet, or you have a specific type of boundary condition that you want to set. That's how, the way that the boundary conditions are set in Saturn is very particular, so we'll explain that later. You have also CS user physical property, which is what we're going to use in the next tutorial to change properties in the domain. So this can change because of temperature, for example, or as you will see in the tutorial, we're going to change the properties depending on the material. CS user initialization, obviously, self as well. Sometimes you see that in the newest version, some of these are also in C. That you can use either, depending on what language you prefer. CS extra operations is another very useful subroutine because it doesn't do anything, but it's called at every iteration. So you can do any sort of operation that you want to do at any given iteration that is not necessarily completed. So, for example, you can compute things like if you want to compute nozzle numbers or forces or friction coefficients or things like that. You can do that. And there is the CS user post-process subroutines, which are basically the ones that you will modify if you wanted to change any of the writers or the part that we were just discussing before. So you will create new parts. You can create new parts based on very complex functions. So say that you want you're for example using a concentration of a species and you want to just plot some cells that have a specific value, for example, or you there's an example of how to change from Cartesian to cylindrical coordinates, for example, things like that. And CS user source terms is also used in the next tutorial. It's the equivalent of what you were doing in the graphical interface of adding the momentum source term, but you can add source term to all the equations, not just the momentum. So you can have for all the scalars like temperature or concentration, but also turbulent variables, k, epsilon, omega, etc. So you can see this allows you to do much more than what you can do in the graphical interface. So at the beginning of all the subroutines, you'll see that there's this generic header, which tells you which version of the code Saturn you're looking at. And it has the GPL license statement. And then you have a brief description. You'll see that all of these comments, these things that starts with a backward slash is these are things that are picked up by Doxygen. So there's an automatic Doxygen documentation created for Saturn, and all of this gets picked up by that. You can see an example in the website, but also if you install Code Saturn in your machine and you have Doxygen, you can recreate your own Doxygen documentation. And I'll show it to you later in the actual website. So after that, you have a list of arguments, normally what goes in and out of the subroutine. In this example, you have the name of the variable and a brief description of what it does. One thing to take into account when you're programming in Code Saturn is that most of these things come from when it was written in Fortran 77, about 20 years ago. And one of the limitations was that the variables had to be maximum 6 characters long. So you see things like this ICO DCL, for example, which is not really pretty name, but it comes from that limitation. Nowadays, if you see the C files, for example, they have much more normal names that are more useful. Then you'll have the proper declaration of the subroutine. You have the name and the variables, and then you have module files. Okay, so all of these module files, you can see them in the source code. So you would normally not need to modify any of these. It's just fix. And then you have the local variables and the argument declarations. When you'll see in most of the CS user subroutines, you have some statements like these insert variable definitions here, where you can put whatever you need to put. So some important things to remember. Code shuttle is double precision. So we always declare variables as double precision rather than reals. Just put it .d. As I was saying before, for this old name limitation, most of the integer variables start with I. So when you see something like that, you're pretty much certain that that's an integer. As I said before, when you compile, when you're running and it goes into the compilation stage, you compile anything in that directory. So you can have your own subroutine there. Anything that is f.f90 or .c will be compiled, so you can have your own subroutine, that your own function that does whatever you want, and it will be compiled there. It doesn't have to be only the source code. If you need anything to be read, such as, for example, inlet profiles or some table or something, you can put those files in the data directory, and it will be automatically to the execution directory. So when you're programming, you can assume that that file is going to be wherever the code is being executed. So you don't have to put full paths for any file that you want to read. The same applies for writing. Anything that you program to be written will be saved in the execution directory automatically with the name, so you don't need to put the full path either. There's a very useful command from Code Saturn, which is compile, that we use to check that what you've written is correct. It doesn't do anything else. It doesn't run. It doesn't use any of your allocated CPU time or anything like that. So it just checks the compilation and gives you any errors or warnings that might be problematic. This is very useful. As you seen yesterday, you submit a job in a big machine, and then you have to go into a queue. And then by the time you have the resources allocated to you, you might get a compilation error. It could be 2 hours after you submitted the job, or the next day or something. So it is very much recommended that before you submit anything into a big machine, you Code Saturn compile, so that you don't waste time, basically. So here's a list of some of the main variables. The full list is on the documentation. You'll see that most of the subroutines have ndim, which is the number of dimensions, which is always 3. So, no, very interesting. Ncell and nclet are the number of cells in cell. So for each MPI task, when you partition your domain into different ranks, you have a number of cells per rank. Charles will explain you that later in more detail when you see the different partition types. But the end cell is the amount of cells that are in that particular rank. End cellet are those cells plus the ghost cells, which are used to communicate between the domains. So the ghost cells are cells that are deleted to make sure that both partition mains can exchange at the same values. En fact is the number of faces, en favor is the number of boundary faces. So everything in Saturn in terms of faces is split between internal faces and boundary faces. So you see that all the things that are things like face area or normal vector of the area or any value that is stored at the face it's either for the internal faces or for the boundary faces. So there's a clear separation between those two. Inva is the number of variables. So obviously, depending on your problem, that's going to be different. If you have, you're solving, for example, for the temperature or for the species, or you have two equation turbulence model or a Reynolds stress model, all of that will change dynamically when you start running. So, and FML is the number of families for boundary faces, for example, and NPRFML is the number of properties per family. Get to that in a minute. NSCAL is very useful. Is the number of transported scalars. So these are scalars that are resolved by the code. So you have a transport equation for these scalars, not taking into account any turbulence variables. So it's things like temperatures, species, all the scalars that you solve in the combustion module, for example. So in terms of geometry, you have very useful things to know, things like coordinates. So XYZ is the XYZ coordinate of the cell center. So you're programming something that you need to know where it is. That's how you get the coordinates. Similarly, for the internal faces, annoyingly, it's not XYZ FAC, it's CDG FAC, because that means center of gravity in French. And as I said before, you faces and one for the boundary faces. So these arrays are all depending on the number of cells, of course, the number of faces. It seems like the slides have frozen. Sorry, something's wrong. Just give me 1 second while I load this up again. Please. Okay. Can you see the slides now?
Yeah, we can see them, yeah. It's at the level of surfboard
Okay.
and fabo.
Okay. Okay, sorry about that. So yes, surffac and surfpo have the. It's going again. I don't know what's wrong.
One, actually, we can see the slides. I don't know if you can see them, but we can.
Hello? Can you hear me?
Yes.
Sorry, I don't know. I got disconnected. Okay, so I was saying, surffac of surview have the vector, normal vector to the face. So the size of the length of that vector is the area of the face. So that's very useful when you need to compute things that are averaged by the area. Things like, for example, forces and things like that. Then you have volume, which is the volume of the cell. So as we said before, this is a finite volume approach, so it's integrated over the volume. So you're going to need the volume every time that you want to compute any source term, for example. Then if a cell and if a bore are two arrays, are very useful because they have the connectivity between cells and faces. So this is an unstructured code, which means that we don't have connectivity between cells. We only have connectivity between the face and the cell. So for each internal face, you will have two cell centers, one on each side, and for one boundary face, you will have only one cell center. And that's how we solve the equation, is integrating over all the faces that belong to a cell. This could be any type of cells. So it could be number of faces per cell. Yes, the cells are identified by a number that goes from 1 to the number of cells in that processor. So when you're programming, that number is a local number. So it would be cell number 1 is different in processor 1 than processor 2. Okay, so I'll get into that parallel bit in a second. I don't know if that answers your question. Yeah. And it's the same with faces, of course. So in terms of variables or properties, the way that it's written in Saturn is by using what is called the code Saturn field, or CS underscore fields, which allows the field to have much more information about the variable than just its value at the cell center. So the field will have several parameters, such as, for example, you can find out the precision of the solver for that particular variable by calling some part of that field. You can have the gradient reconstruction method that is used for that field. You can have a lot of information for a field rather than just having a bunch of arrays for all those settings. Call it. So each variable has an index, and then that index is used to create a field at the beginning of the calculation. This page in the documentation in Oxygen will show you in a bit, where it has all the indexes of all the variables. So in this example here, IPR is the index for pressure, IU is the index for velocity, and ICP is the index for a specific heat. So here in this example, you see you have a first call to field get value of a scalar. So that is you see here, this is for a scalar. So if you want to get, you have to differentiate between vectors and scalars in code Saturn. So that's basically, you call this function, and this IPR is telling you that what you want is the pressure, and then it's going to be stored in this array, zero pressure. Okay, so now this number IEL is this cell number, and that would give you the pressure at that cell. Okay. Similarly, here for the vector field, which is the velocity, you store it into this array in this particular subroutine, and then you can have all the components in this way. Okay. And here you do the same for the CP. Okay. You'll see that in the examples that we're going to do later. In C, something similar. It's just that it's done this way. So CS underscore F underscore, and then you change that name for whatever IPR, IU, etc., whatever variable you want. And then you can get the values like that, like what's written here. Things to remember is that in C, your indexes start at 0, whereas in Fortran begin at 1. So your loop is going to be different, or your counter in the loop is going to be different. As I said before, if you go here, you'll see a much more detailed explanation of how to use the fields in Saturn and how to get any property or any variable that you want. Or you can look at the actual files in the source code, these two files, which have all the list of all the possible things that can build up in the code. And of course, this being an open source, you could put your own if you want. So here's an example of how to change the density as a function of temperature. So imagine that you have an equation like it's written there, a quadratic function of the temperature. So for this, you will need to get the field for the density and get the field for the temperature. So that's what we do at the beginning, is declare those pointers, one for the scalar temperature and one for the density. Then we get the index of the temperature scalar. This is like a shorthand notation. You could have many scalars, so you could have not only the temperature, you could have things like species concentration, or you could use another scalar to compute another temperature field that it has different boundary conditions in the same calculation, for example, if it was a passive scalar, or any of the specific physics scalars that you can have. So to get the temperature, then the trick is to use I don't know if you can see this ISCalT is always going to be the index for the scalar of the temperature. Okay. So then you call field get value these two scalars, one for the temperature and one for the density, and then you'll have the two pointers that we had at the beginning declared. We put them here. Then these are just constants. These are the A, B, C constants, and these depends on your equation. And then what is done here is a loop from IL is the index. It could be II, JJ, KK, whatever you want. You will see that in the Saturn examples, or in general in the code, they tend to use this to do loops on the cells, and IFAC to do loops on the faces, rather than just generic names like I, J, K, L. And then you do the loop on all the cells for this particular processor. So this would be the number of cells locally. You get the value of the temperature right here. So for that particular cell, we have, this is going to give us the temperature. And then you set for this particular cell again, you set the density, which is now being shown here as your equation. So A times T times A times T plus B plus B. Okay. So this example would be in CSU's physical properties, which are the ones that change viscosity, density, CP, etc. There's another example here. This is how to initialize the temperature. This would be in CSU's initialization. This first test here, I suite is an index that it tells Saturn whether you are restarting a calculation from a previous one or not. So if it's equals to 0, it means that you're restarting. So this will be only done in the sorry, if this is 0, then it would be done at the beginning of the first time step. If not, then it's not done, because it assumes that you're restarting from previous calculation, and therefore you have a value already set that you don't want to change. Then you do the same. You call get of a scalar for the temperature. So this is the index of the temperature is fiscal T, and then you put this into point, and then you do a loop on all the cells and set to the value that you want. You could do it differently. You could do a loop on the cells and then only select the cells that are in a certain part of the domain, or you can select them geometrically. For example, if you want to say all those that have x equals to larger than 0, for example, or anything like that. This other example is to initialize the velocity. So now we call the fitted value vector function with the index for I. There's no IU, IV, IW. IU is a vector already, so this is one. And then in this case, you have a function that depends on time. Okay. So this TT caps is the time in seconds. Okay, so as I say, for the boundary conditions are in CSS boundary conditions, and by the end of this subroutine, when you there's going to be a check, and every single boundary phase needs to have been assigned a type of condition. So if you're not using your graphical interface, you will need to do this for all the boundaries, and if you don't, you will get an error saying some boundary conditions haven't been set. And so for each phase, you need to define a type, which will be this I type FB, and the type of boundary condition and the type of and the value of that boundary condition. Okay, so the possible types are inlet, wall, rough wall, symmetry, outlet, or undefined. Undefined meaning that you're going to set it yourself to something that you want. So the first ones are the ones that you would normally set on the graphical interface. And that allows you to save sometimes once you set the type, like for example, if you set a type that is outlet, then it automatically fills all the rest of the arrays that you need to set for your boundary conditions. Whereas if you set an inlet, for example, you still need to set the value of the inlet, or a wall, for example. So if you set a wall heat flux, for example, you need to fill in the arrays for this type of condition, because you could have a heat flux or you could have a fixed temperature. But because you say that the type is already a wall, then the code will know that the velocity has to be 0 at the wall. So you don't need to set the velocity, but you still will need to set the value of the temperature, for example. Okay. So, and as I said, I and DEF is undefined. So you can put your own precondition if you want to use something that is non-standard. So another useful function in CodeSat to set this boundary condition is the function get FBR. that is the equivalent of your graphical interface setting when you were yesterday setting inlet or outlet. The moment that you define the names of the boundaries is something equivalent to this. So you could have, depending on your mesh, the mesh will have, or the mesh can have groups of faces with names or numbers, and you can use those to select faces, or you can do it with some geometrical parameters like x less than 0.01, or you can use functions like faces that are in a plane or inside a sphere or a box, or whose normal vector is this or something like that. The important thing is that you select a subset of faces where you want to impose those boundary conditions. So you can use this function getFBR, and that you set criteria, selection criteria, yeah, and that will return a list of all those faces that comply with that criteria and the total number that are found in that particular processor. Okay, so this is all done locally. So then what you need to do is loop from 1 to the number of faces that you found and set the boundary conditions on those faces. Now, the correlation between this will go to 1 to the number 1, 2, 3, 4, 5 until whatever number of faces you found, but that's not the number of the face. So the face has its own number, and the way to find that number is to use that list that is returned from this function. Okay, so that list has the real face number. So now with this statement, you get number of the face, the real number of the face for that face in this subset of section criteria. And in this case, what you see here is that this cell, this array, as I said before, is the connectivity between that face and the cell center of the boundary, if needed for anything. So now that you have the face number, you can set the boundary condition using the arrays. In this case, we're setting the velocities to 1.1, just an example. And the type is set as an inlet. Okay, this means inlet. This face corresponding to cells. These faces are, when Saturn reads the mesh would have nodes and connectivity between those nodes. Saturn creates volumes and creates cell centers, computing the center of whatever type of cell it is, and computes faces, creates the faces, and creates a face center, and then numbers all of these things that are created. So the face number is what would correspond to the mesh face that you would see in a normal mesh, but the actual mesh file doesn't have a face number. These numbers are created by Saturn. The same way the grid doesn't have a normal vector for the face, for example. So Saturn computes the nodes that create a face. So it's a triangular face. It has the 3 nodes and computes the plane from those 3 points and computes a normal to that face and computes the face center. So all that is done at the pre-processing stage. So when that's done, that mesh file that is created intermediary has all this information, and that's fixed. But that face, all those faces have their own numbers. When you partition that, then they are renumbered into the smaller domain. So all say that you have 1 million cells and a partition into 100,000 cells. So for that particular processor, the number of faces goes from 1 to 100,000. And that's what this IFAC is. Okay. So IFAC could be anywhere between 1 and 100,000 in the example I'm making. And similarly, the cell number is also local. And here in the other example, we're setting a outlet. So this is an outlet, and as you can see, because you set it as a type that is outlet, you don't need to fill in any of these arrays that have the value of what you want to put. It automatically knows that you have a zero flux outlet boundary condition. Okay, so one thing that you need to take into account that is very useful for people that are using their own subroutines and programming is that Subroutine is a very generic way of dealing with the boundaries. The idea of the philosophy behind this is that in reality, when you build your matrix, they don't want to have to change the matrix because of the values that you impose at the boundary. So instead of changing the matrix for your cell centers with the values at the boundary, these boundary conditions are treated in a way that everything is treated the exact way. So in this example, this is a random cell, which you have I would be the cell center, F is the face center, and sigma I is the volume of the cell, and SB is the surface of the boundary face. Okay, so what we would normally do is create this I prime point, which is the projection of I into the normal face. Okay, and that allows us to do things like boundary gradients and things like that. So when you fill these CS user boundary conditions, what really happens is that all the boundaries are written as a function of A and B coefficients. Sorry. And regardless of whether you have a flux type of condition or a fixed value type of condition or a mixture of those, you will have A and B coefficients. And whenever you want to find out the values of those boundary coefficients in a subroutine, say that you want to calculate pressure at the boundaries, for example, you can use these A and B coefficients to obtain the value of the boundaries. So you'll see that in the tutorial that we're going to do, you're going to have to compute the heat flux through the boundary, and rather than using the value that you impose, you will have to get it from the code, and I'll show you. So as subroutines that some post-processing subroutines that allow you to do these kind of things much easier, like post-boundary thermal flux, post-boundary temperature. that basically gets you those functions. Well, you
Juan? I cannot hear you anymore. I don't know if the others can hear you.
No, I've lost Juan here as well.
Just 1 second, I will check on the other chat. Okay, now
He's left the session apparently.
Yeah, I can see that it's disappeared from a few places, Juan. I don't know, maybe he has got something in his internet connection.
Yeah.
I don't know what's happened. Also, Charles left. I cannot see Charles anymore.
No, I mean the list of the attendees because I had to reconnect. Juan had just, I mean, his computer. He just had to reboot his computer. So just
okay.
take a few seconds. Okay, to comment a bit on what Juan was saying before, and some question in the chat. You know, you've got some arrays are defined for per subdomains. I mean, without including the extra ghost cells or the periodic boundary conditions, and these correspond to arrays defined with n cell. And when you want to include as well these inner cells and the periodic or the ghost cells, you have to define the arrays n-cellet. I also added in the chart is that some arrays, I mean, it's not visible in the fortran part, but in the C part, some arrays are defined as in 32 bits. So those are mainly the binary condition arrays. And the cell ones are usually defined in 64 bits, because when you got meshes of let's say 2 to 300 million cells, the connectivity between the faces and the cells, and the cell and the faces can be over 2 billion, which is actually the limit for 32 bits. So when you install the code, there's an option to go for these 64 bits. But now in the recent version of the code, this is set by default. So if you look at the C part of the code, you might see some differences. So I mean, the 32 bits correspond to LNUM and the 64 bit to GNUM. It's also worth it reminding that the periodic boundary conditions are actually not periodic conditions. They are not boundary conditions. The periodic boundary conditions are actually treated like ghost cells. You see that the same type of ghost cells you would have when you do parallel decomposition. So that's why it's treated differently. You can see that in the GUI is set up at the mesh or preprocessing stage and not at the boundary condition stage. And this is also used for mesh joining, for instance. Okay, I'm going to try to take over Juan as he's trying to join. So in the next part, this is about parallel consideration. So that's basically what I was just saying. And as soon as Juan has joined, I mean, I think he's back in.
Hello, can you hear me?
Yes, we can hear you.
Yes.
Yeah. One, just to let you know, I just
that.
passed to the next slide. I just passed to the next slide. Just to...
Okay. Thank you. Sorry about that. My computer decided not to stop working for some reason. Okay. I think we need to move on. Quite late. Just a quick word on this parallel considerations. As we were saying before, when you're running on this big machines, you need to split your domain into different parts, and the way that certain treats is by creating what they call ghost cells, which are basically mirror images of what's on the corresponding processor, like this picture. So the gray cells are going to have the same information as the corresponding cell on the other side. So that's why you have different number from end cell and end cellet. Similarly, periodicity is treated in a ghost cell kind of arrangement as well. That's why the effect of how you partition your domain is important, and you will see that later. Computational uses mostly MPI to communicate with different domains. we also have OpenMP, but what you've been doing so far is all using MPI. So all of the normal codes for MPI that you will have in any MPI implementation are wrapped. And so we have wrappers for things like MPI all reduce and all those things. So we have specific functions in Saturn that are much shorter and easier. There's a full list of all of these functions in CS user extra operations in one of the examples for these parallel subroutines. In terms of C, as I said before, there's a lot of C now in the code, and there will be more in the future. I have 41% here, but I think now it's more like 50%. And everything that is being added to the code nowadays is being added to C subroutines. So there's going to be more and more subroutines. Here are just some of them. Here are some examples. So CS user coupling, all the coupling that we do with code Saturn and external codes or within itself. Code Saturn with code Saturn is always done through C using a library called PLE. You can use some CSS parameters that see you're going to use that in the next tutorial. You'll see that for conjugate heat transfer. There's a lot of things that you can do to the mesh in CS user mesh. So you can use Saturn to extrude the mesh. You can use Saturn to refine the mesh. You can create like a boundary layer refinement, for example. You can scale the mesh so that you want to change whatever your mesh is in millimeters to meters, for example. You can do that directly in Saturn. You can join different meshes. So there's a lot of options there. Another thing that you'll use later is CSS performance tuning, which allows you to change the settings for things like partitioning. CSS post-process lets you write new writers or new parts as well. Or you can even write your own version of the solver by using cssolver.c. So there's quite a lot of things. Again, you can have more details in the work and documentations. Similar to the Fortran subroutines, you start all the subroutines with some comments, okay, and with the license statement, and then you have the includes, and have the locators as well. Then, as it's starting, see, you will have your definition of additional functions at the beginning, and then you will have your begin C declarations. So create your own functions. You have a function called BFT malloc for memory allocation. Equally, you have a BFT free for bring down, and also BFT printf, the Saturn printf, but it will print you directly into your log file, your listing. And I guess that's it. No.
Juan?
Okay. Yeah.
Ah, okay, you're there.
Yeah. Can you hear me?
Now, yes.
So does anybody have any questions?
There were some in the chat, but I think we answered them. I mean, otherwise, just feel free to add more in the chat, okay?
Yeah. So now we're gonna go to the next tutorial, which is an extra step from what you did yesterday, in which we're gonna try to add heat transfer through the solid of what will be a heat exchanger in this case. So it's the same configuration of what we did yesterday, except that now these cylinders have a thickness. They are steel cylinders. And the idea is that you follow the instructions to compute now this conjugate heat transfer. So you will have to add the temperature. You will need a different mesh, a mesh that contains the solid, basically. And you would need to set the boundary conditions and the properties of the solid as well. And tell CodeSaturn where the solid is, which part of the domain is solid and which part is fluid. And that's done through subroutines. Okay. So the first part of this tells you how to set up the case. It's very similar to what you did yesterday. And as someone pointed out yesterday, you can just copy the previous one and change what needs to be changed. And at the end, you'll see that there's difference in the boundary conditions because you don't have a boundary conditions for the solid. There's also difference in the volume zones. You have now a fluid zone and a solid zone. And you'll need the checkpoint directory from your simulation, the one finished last night or earlier this morning, to restart from that and continue computing all the fields, but this time including the temperature. And once you've done your graphical interface file, then you'll move to this section that explains what you need to do with the subroutines. If I can make that bigger. So there are three subroutines that we're going to use in this tutorial. CS user parameters, which we're going to use to differentiate the solid from the fluid. Because both zones are in the same mesh. The mesh that we're giving you have everything in it. So it's just a portion of the cells have a tag that is called solid, and another one has a tag that is called fluid. Then CS user physical properties is used to change the properties because now there are parts with different properties of the domain. They are not function of the temperature in this case, but they're only function of whether it's a solid or a fluid. And CS user source terms. Yesterday you put in the graphical interface a source term for the momentum that was driving the periodic flow. Here we're putting a source term of for the temperature that is gonna remove the heat that you are inputting through the solid. Okay, so it needs to compute the mass flow rate and the heat flux, and then add a source term that would remove that energy. Okay, so you'll see that for each subroutines, there's a description of what you need to do. There's we'll give you the line number, and basically you're going to copy the empty files, and then you need to put this into the empty files and that line number. So this is only a few lines for this subroutine, a few lines for these physical properties when you have all of these values for the solid, so density, conductivity, and CP. And in source terms, it's a bit more to do there, but as I said, you calculate first the mass flow, and then you compute your source term. Okay, so everything is commented. I've tried to put some explanations in the subroutines, but if there's obviously if it's something that you understand and you want to know more, just ask. So, and it's going to be the same thing.
Juan, in case someone didn't manage to run the simulation yesterday, is there somewhere the checkpoint, a standard checkpoint where they can restart?
Yes. If you didn't manage to run the simulation yesterday, we have a checkpoint. I'll show you in a minute because I need to restart my virtual machine, so I can show you where the checkpoint is. But the first part is all done in the local machine. Okay, so you can start with that, and then I'll show you in a minute where the restart is. That's a good question. Are we still having a coffee break at 11? It is 11 now, but we are actually quite late. So I would encourage you to get coffee if you want, or tea, or anything, while you work on the tutorial as well, because we only have the reservation for the machine until 1 o'clock. So ideally, you will be submitting the job and doing some iterations before that reservation is finished. So yeah, I think we should merge the coffee and the tutorial, if that's okay by everybody. Okay, for those who don't have the results from the tutorial yesterday, you can copy the checkpoint from the shared directory, which you can see in the screen, hopefully now. I'll put this in the chat. Yes, that checkpoint directory in the virtual machine is the same. The advantage of it is that the other one is already in ARCHER, so you can just copy it from there rather than having to do the remote transfer of the file, which is quite big.
Okay, I know you are all busy with the third tutorial, but I'm just going to introduce you shortly the fourth one. So you can run that after the course, actually, because you continue having access to the machine. So I'll just give you a short introduction to explain one we're after in this fourth tutorial, which is about tuning the code. and about looking at the influence of the partitioning to the time to solution, basically. So a lot of things in there assume that you've been running the previous tutorials. So, I mean, for instance, we don't write explicitly copy files, but we ask people to copy some files, but we don't show the path. So it's just down to you to do that. But so basically, it's about looking at as I said before, the type of partitioning and the partitioning tool you use, and its influence on the time to solution. And then there's also another feature in Code Saturn. So it uses MPI for communication between processors. So when the subdomain are distributed across processors, of course, but there's also a feature based on OpenMP, which is used to, when in the case of shared memory, for instance, on a subdomain, you can divide the subdomain in a few threads. And hopefully, when you combine MPI and OpenMP, you can get some speed up. But this is extremely machine dependent, and is also configuration dependent. But these are tests you should be running just for a few minutes. Basically, each time, before going for production, you should run this test. You first need to know and to be sure that the simulation you're going to run, I'm not talking about the tutorials now, I'm talking about in general. You need to be sure that the simulation you run is okay. And then you need to check which partitioner are going to be the best one and which combination of MPI and OpenMP is going to be the best one. So basically, there are several tests to run. So some partitioners are embedding into the code, like the geometrical partitioner, so based on space filling curves, like Morton and Hilbert. And two extra partitioners have been plugged into the code for this exercise. So it's PT Scotch and Parmetis. And so the idea is to use user subroutines. So the user subroutines is called user performance tuning. So sorry, which is here is in 2.2.2 CS performance tuning. And then you add the gray box into the subroutine at the right location. And you can see that there are two lines, CS partition Scotch and CS partition Scotch. And these lines, the simulation has to be run with that. And then this has to be changed to partition Metis, and then SFC Morton and SFC Hilbert. So the idea is to use the first tutorial, but starting from scratch, so you don't have to use the checkpointing. And I think we ran for only 100 time steps. So everything is done on the remote machine, and you should get at the end a comparison of time steps like this using a small tool called collect_timing.sh that you also hopefully should have access to. So you just type that in the working directory, and if a simulation are run properly, this should give you the average compute time per time step. So this is a comparison that I obtained on using the different partitioner, but it might be different for you depending on the test case you run. So the important thing there is that you can see that in the case of Parmetis, it's probably 10 to 15% slower than the others. So and 10-15% slower. So if you count simulation, we can last what? Sometimes they can last months for massive LESs. So that's about three days you would save, you see. And then the other part of the exercise is to change the combination of MPI tasks and OpenMP threads, still using only one node. So the three first cases is that the first case is for 64 MPI tasks per node, so the nodes are undersubscribed. In the second and third, they are just subscribed properly with a combination of either MPI and OpenMP. And the last one, we use hyperthreading. And so the timing is computed against in the same way. So these values that were given here are just a matter of information because these values depend on the load of the machine and on a lot of parameters that we cannot control really, but it gives you roughly an estimation. So ideally, if you would perform this kind of test, you would run 3 or 5 of each and take the average timing. And note as well that this test only includes the solver. It doesn't include the IOs. So this is other test or other things you should consider, especially if you think about going for large meshes. So you have to be sure that you configure your test case for the size of the files you are going to dump on the disk or read from the disk, and this depends on the work system, basically. For instance, for Lustre, you can add some striping, and this really helps. You can multiply the writing and reading on the disk by 2 to 5 sometimes, depending on the size of the mesh. So yeah, so that was just a short explanation of what should be done there. I would suggest you, if you're interested in checking this, to do that after the course, because you would use another installation of the code, which instead of typing code underscore Saturn, you will have to type code underscore Saturn underscore with libs. So it's in the first block here. This allows to access ptscotch and parameters. Basically, it's not installed in the other case because Saturn tends to use as a default ptscotch, and in our case, as you can see here, ptscotch is a little bit slower than Morton that we've been using. So we've been saving some CPU time doing so. So yes, and you will be using another submission script for running on using OpenMP, here. So that's for the test comparing the MPI and the hybrid MPI OpenMP. So you'll be using another queue, and so another submission script and then another queue. So, but I also advise you to do that after the course. Are there any questions? Okay, so somebody raised a hand, so maybe we could use a microphone. Okay, so if there are no questions, just continue on the other test case, on the other tutorial, sorry. And around 11:45, we will explain you how to stop nicely a simulation. Okay, because we are reaching the end of the reservation allocation, which finish, and this reservation finishes at 1 o'clock. Basically, you are not going to be able to submit jobs any longer using the submission scripts after 1 o'clock. And the job you've got currently running in that reservation are going to be killed as well. So there is a nice way in CodeSaturn. So this is a slide I'm sharing. I hope you can see it. So there's a nice way in CodeSaturn to properly stop a simulation. So basically, you go to the working directory on ARCHER2. So this one, which is a combination of year, month, day, and so forth. So in that directory, there's an R missing here. A new file called control file has to be created. So you basically edit it using emacs-gtk control_file or VIM and the control_file. In that file, you put a number as small as possible. Here is I put 29. You have to put a number which corresponds, which is smaller than the number of iteration your job has been running, because you've been supposed to start running from 30,000. 29 is much smaller, and so you save that file, control_file, and the executable CS solver is going to read it and interpret it as a finishing iteration number or maximum number of iteration of 29, which is smaller than the current iteration that the code is running on. And that's going to stop the simulation and dump all the files in a nice way. So you are going to get post-processing, monitoring, and checkpoints, and as well the end of the listing file. And at the very end of the listing file, at the bottom, very bottom, you should get something like end of simulation or end of calculation, which means that the simulation finished properly. So I put this number 29 to be sure that it was smaller than what you were running, but you can adapt that number to, I mean, what you would want, you know. You can just look at the current iteration and put it in there as well, and just add 1 or 2 or 10 to that number and put it in there. But just to be on the safe side, just stick to a very small number. Are there any questions?
One thing that you should take into account as well is that control file has a lot of other uses. You can look at the documentation. You can change many things on the fly while the code is running. So you can change, for example, how often do you write a checkpoint, or how often do you write a post-processing, or how often do you do many other things, as well as forcing them to be written when at a given time step. So if you want to know more, you can find that in the user guide. It depends on the queuing system, Ian. I can't remember which ones are supported and which ones are not, because it does check depending on the queuing system, but I think for Slurm, not too sure.
I think there were some issues.
Sorry,
Sorry, Juan. I thought there was. I think there were some issues with PBS as well. So that's why it's better to control manually. You know, to be fair.
Yeah, I think there was.
Yeah, at the moment, the capability is there to get the stop signal from the queuing system, but a lot of times it's not working. I remember that, for example, on Hector, it was working, and it was possible to automatically get the signal from the queuing system and properly stopping the simulation. From ARCHER2, Archer, it was not more possible, and you need to manage yourself setting properly the number of iteration for your simulation. I don't know about ARCHER2, and it's the same for other system. About the elapsed time, I don't know.
No, you cannot stop after hold time. What it's implemented in is that the queuing system that you have normally has a variable that tells you what's the hold time, and it keeps checking against that and takes an average of the time per time step and then stops that, but it doesn't know beforehand what's the hold time. So it's just basically saying give you twice the amount of time that you need for a step in the last 10 time steps or something like that, and it stops it. You can do it by time in seconds, meaning like if you have a on-a-steady simulation running, so it's equivalent of iterations, but not hold time.
Okay, for the one running at the moment, I would advise to read this slide that we're sharing and to do that, because you only have, I think, 6 minutes to complete your job. Otherwise, you're not going to get any out of it. Okay, I have removed the reservation from the submission script now. So what it means is that if you submit a job, now you go to the normal queue, so it might take much longer to run, but you'll still be able to run the jobs. Okay, I think we're reaching the end of this course. The reservation being finished now, as it's 1 o'clock. So we would like to thank you all for attending the course. And if you have any question, you can still contact us through email. And there's going to be a catch-up session on March 24th at 2:30, if people would like to join. So we all hope you had enjoyed it. And I think we are going to close the course at the moment now.
Thank you very much.
Yeah, thanks a lot to all you.
Thank you.
Thank you. Bye.
Bye-bye.
Bye-bye.